Hey guys, Mr. Blue here with another at-home video lesson here. Just recapping today, what is the actual evidence here that electrons actually exist in these particular shells? So just something, maybe an observation that you've made in chemistry so far is basically that different elements, when they're heated, will give off light. So in the case of magnesium, it's going to emit that really strong white glow. Now, we, in our human eye, we detect white light. But white light is actually made up of a mixture of 7 different colors, or the 7 different colors of the rainbow spectrum. And what we usually do to remember that is Roy, G, Biff. Okay? So our highest frequency light is down here, and our lowest frequency light is down here. And together, we call that light a spectrum, like this. Okay? So all of the different things that we're going to detect in the world is going to be through what we call that visible light spectrum. So, as I've said, right, different metals here are going to produce different colors. And this is really helpful for chemists because it can help to identify elements in the lab. And it's also used in terms of fireworks. So what evidence we have of this is something called atomic absorption spectroscopy and something called atomic emission spectroscopy. But we're going to be more focusing on the emission aspect today. And the 2 terms that you guys are going to need to learn are the excited versus the ground state. Okay? So what we get here, right, is let's say, for instance, we have a element. Inside is a tightly packed nucleus, and then we have our 2 energy shells. Now, let's say, for instance, okay, let's draw, say, a lithium, okay? Now, we know that lithium has 2 shells on the outside. So what you're seeing here in this little GIF, right, is that what happens is we've got 2 electrons on the inner circle and then 1 at that next energy level. Now, when we heat this, okay, which one of these, according to Coulomb's law, the one that's furthest away from the nucleus is the one that's going to be more likely to react. Now, at the moment, right, we go, well, where's the 3rd shell? It's actually there, okay? But in terms of lithium, it's not actually in use until what's going to happen, right, is that let's say, for instance, we get a piece of lithium and we add energy to it. Then what's going to happen, okay, and here's our energy. What's going to happen is that the atom will absorb that energy. It's going to absorb certain energy. And what's going to happen is that electron is going to be activated here. At the moment, it's in what we call its ground state. But what's going to happen is it's going to become activated and move up a level very, very quickly. Okay? So what it did was it absorbed energy here to move up that energy level. But the thing is, right, is that eventually, okay, energy is always contained. Okay? Energy is always transferred and not destroyed. So what's going to happen is that lithium doesn't like being in that state. So what will eventually happen is it's going to fall back down. So here it is on this side, and now it's excited, and then it's going to fall back down to its level. Now when it does that, these levels on the outside have got higher energy than this level. So what's going to happen is it's going to produce some energy, okay? And that energy is going to be released. Now we can quantize that energy. It's a pretty simple equation. We don't really need to know much about it, but it's simply the fact that E equals hV, where we have E is energy, H is what we call Planck's constant, and V is the frequency of the wave. So on this side, right, we had absorption. So that is where we are going from what's called a ground to an excited. And then on the other side, we have emission, which is where we're going from excited down to the ground state. Okay? And when that's going to happen, we're going to get the release of energy there, like that. One of these pens are great. Okay? Now, why is that important in chemistry? Well, because each element has a unique structure of electrons, then each element gives out a signature release of energy. That energy is going to be quantized according to that. So here's another way of thinking about it, okay, is that let's say, for instance, we have an electron there at the ground level, at the 1 level. Let's say it's a simple hydrogen atom. Then what's going to happen is when we excite it, it's going to move up to this 2 section. Okay, it's going to move up to the 2, and then it's going to fall back down. Now, just like, right, let's say you move up a ladder, then what's happening is you're adding gravitational potential energy to yourself. The further up the ladder, the more damage you're going to do when you fall. So what happens is if we fall from the second rung of the ladder, as atoms like to do to come back to normal, then you're going to release a certain amount of energy. Okay? Now, the more electrons it has, the more complicated it gets. Now, here is what we see as a result. So on the left-hand side, when we're putting energy in, we get your atoms absorb particular quantities of energy. But then when they're emitted, they release specific bandwidths of energy. And we can use what we call a spectrograph or a spectrometer in order to measure and look at these particular elements. Okay, now what that means, okay, is that all of these particular elements are going to have a different flame color. It's sometimes a little bit hard to see in the lab, but here are some common ones here, okay? And we can work these out by just doing a simple flame test, which is what we're going to do in class here today, okay? Hopefully this helped your understanding of some of this. I know it's an important concept. It's one that's not overly emphasized as much, but here's the key takeaways. Electrons exist at specific energy levels. Atoms can absorb energy, okay? They absorb the energy, but then they tend to release it. When they release it, each atom has a unique spectra, one of these things here, okay? And then finally, it's very helpful in chemistry for quickly identifying metals in a process called flame testing. All right, thank you very much for your time today. That will be all from me.